So our next speaker is going to be Olteanu from University of Oxford. He will speak about the dichotomy, another dichotomy, for queries with negation in probabilistic data.
Thank you, Val. I would like to thank the organizers for inviting me. This talk will essentially build on top of the previous tutorial. Essentially, we'll try to look a bit at the case of negation, right? In the previous tutorial, what we have seen was mostly we looked at conjunctive queries, we looked at union of conjunctive queries. There was one approach to deal with negation, but negation was only applied to relational symbols. And now the question is, what happens if we have negation somewhere else in the query? It is just a preliminary work in the sense that the picture is not clear, is not completely clear, but at least for some fragment of first order logic, we have a good picture of what's going on there. And I will just shortly overview some notions of probabilistic databases. Hopefully they are actually still clear in your head from the previous tutorial. I will only use so-called tuple-independent probabilistic databases, which are exactly the type of databases Dan Suciu talked before. Essentially what this means is that you have a normal database, but with every single tuple you associate a distinct random variable, and this is a Boolean random variable, right? And this random variable gives the probability for that tuple to be in the database. So essentially, by setting such variables to true and false, you can think of tuples being in or out of a possible instance of the probabilistic database, right? And if you think that we have, let's say, n possible tuples out there, then by flipping in and out every single one of them, we can get 2 to the n possibilities. Right? And as Dan also argued before, it is not feasible in databases to simply iterate over all these possibilities. Right? So what we'd like to do, if at all possible, when given the query, to try to evaluate this query on top of this probabilistic database in a time which is polynomial only in the representation. In this representation as a database with the probabilities. Right? And not in its expansion in the set of possible worlds, because this is exponential. Okay, so that's essentially what I want to say here. And how you can compute the probability of a world? Well, you look at the variables in the database you have, right? And you take an assignment, let's say, of a total assignment over the variables that defines the world, and then you take the product of the probabilities of these assignments. If x1, for instance, is true, this means the tuple t1 is in the database. If x2, for instance, is false, this means that tuple t2 is not in the database. And then if that would be the only if this would be the only tuples we have in the probabilistic database, then the probability of that particular instance will be the probability of x1 being true multiplied with the probability of x2 being false, right? So that's the setting. It's a very simple model. As language, I will start with the language which arguably perhaps is not very pleasing for logicians, but I will actually discuss also the case of languages closer to your heart perhaps. I will start with relational algebra, and I'll try to motivate this towards the end, why I started with this. This is a popular database query language since code time, since 1970. We have as algebra carrier the set of all finite relations, and then we have operations like projections, Cartesian product, difference, and so on and so forth. When I was saying that I'm looking at negation in the context of probabilistic databases, I really meant here set difference, right? You take the difference between two relations, for instance, or between two subqueries. Yeah? And this is nevertheless as expressive as domain relational calculus or first order predicate calculus. And this is also known for decades now. I will look at a particular fragment of this language, which relates very much to one of the results Dan Suciu presented before. Namely, I look at this language of non-repeating conjunctive queries. Imagine you have, in this case, relational algebra, right? So that is, you are allowed to have, in this particular case, projections. You can do Cartesian products. You can do set difference. You can do joints. You can do selections. But you cannot do unions, right, for the moment. I will come back to the union case a bit later. And we do not allow repeating relation symbols. This turns out to be a headache in probabilistic databases, right? Repeating relation symbols, because you get non-trivial correlations in different parts of the query, because the same relation symbol carrying the same variables, random variables, occurs over and over again, right? So this is the kind of setting we have here, and I will give you a few examples. For instance, so this is a very trivial example that takes a product of two relations, R and T, and also product of U and V, and then takes the difference between them, and then projects away all query variables, right? So in a perhaps more familiar syntax, we say R and T and not U and V, and at the end we quantify over A and B. Right? We say exists A, exists B, such that this holds, right? And we are interested in the probability, for instance, that actually such a query is true. A second query is the one used by Dan in his tutorial to show hardness results. This is a query that joins R and S and T such that R and S would join on a query variable, let's say A, and S and T would join on another query variable called B in this case, right? And essentially this is a symbol for the join. It says I have R and S and T. By reusing the same variable at different places, we really, essentially encode joins, right? That is, R and S join on A and S and T join on B, okay? So that's the basic thing. And the query evaluation problem in our setting is this. We are given a query, and for any tuple-independent database, we would like to compute the probability that Q is true in a random world of this database. And we are interested in the data complexity of this problem, as Dan mentioned before, where we fix the query and we take the database D as input. And we will see that, in fact, it does have an important role in our discussion here, that we consider the query fixed. Good. So, what is the main idea of this? What the main result of this talk is essentially similarly to what Dan showed before for different languages, to show that, in fact, if you are given our language that is this relational algebra with non-repeating symbols, and with difference this time, with negation, then some queries are easy, right? Whereas some queries are hard. For some queries you can just walk, but for others you have to climb to get them, right? And this is actually depicted very nicely here in this sculpture by Gilles Bruvel, where, as you can see, well, it's called, in fact, the dichotomy, where some parts go this way, whereas others go the other way, right? And this is a surprising result, which when Dan proposed the first time in 2004, this result for what he calls now the small dichotomy result for this non-repeating conjunctive query language, it was very interesting, because essentially it says that some queries are very, very simple. You can compute them he says in polynomial time, but in fact the queries, the non-repeating conjunctive queries, can in fact be computed in linear time, assuming convenient sorting of the database beforehand. And all others are sharply hard. So there is a wide gap between the very hard queries and the very easy queries. And there is nothing in between. And it turns out that, at least for the fragment I isolated out of relational algebra, the same idea holds, right? That some are very easy and some are very, very hard. And now the perhaps most surprising result is that this very simple property he mentioned before, namely the hierarchical property, also holds here. That is, this is the property that separates out the good from the bad, if you like, the ugly from the handsome. But this is in a sense surprising for several reasons. One reason is that if I start with queries in my language and I actually rewrite them, I can transform them into relational calculus formulas, for instance, right? And they may have disjunction and they may have repeating symbols, right? So it goes beyond, so the power of this characterization of the hierarchical property characterization goes beyond just the very simple non-repeating conjunctive queries. Okay, so another, yeah, so I think this, so this would be the main, I would say, surprising result. Checking the hierarchical property given a query can be done very efficiently. You can do it in AC0 essentially, right? And why is this relevant? Well, it is relevant because, you know, as a database systems person, if I get the query, you know, my system, my engine gets the query, I can decide very quickly whether I should employ this exact computation technique for the tractable queries, or I should do approximation, for instance, right? Now, having a characterization that is actually not that effective, that would take a lot of time, you know, to look into, right? It's perhaps prohibitive, and you might go, you know, uniformly for all queries with approximation. And we try to understand how far we can go with this language so that we can still get this hierarchical property satisfied, right? So I will present you the definition again, perhaps slightly different, but in fact is equivalent to the one Dan gave before. Namely that if we look at Boolean queries, let's say, yeah, in our language, then a query is hierarchical if we look at every pair of distinct query variables, let's say A and B, they have the different colors, right, red and blue. There is no triple of relations RST such that R has A but not B, right, as query variables, right, R being a relation symbol. Then S has both A and B, and T has B but not A. Right? That is, we don't have this situation in which we have S sitting between R and T. Yeah? This is actually depicted very interestingly by a painting, yeah, showing a dance. This is a Romanian dance called Hora. When I was a child, I was somehow, you know, forced to go to weddings, yeah, to dance the girls. And it was always hard for me because, you know, sitting in the middle and dancing, always synchronizing with the others was very, very hard. Now, decades later, I understand why. It is intractable, right?
You didn't like holding hands.
Sorry?
You did not like holding hands.
No, I like, but somehow it's very hard to, you know, balance them out, you know, to synchronize with the others, right? And now the reason is, it goes beyond just, I mean, if you think of hands just being joints, then that would be the case of non-repeating conjunctive queries. So if you think of these hands also being some difference operations, right? Negation, then that would hold as well. Right? What I can do, however, is this, right? This I can do. I can dance with one partner, right? Or, you know, I actually took the liberty to you know, destroy a bit the original painting of a former classmate of mine. I can take the same picture and can put it at different places and inside itself, right? This means that I can actually do a join here as long as the query variables are actually covered by another relation which does a join with something else and so on and so forth. So these things I can do. So these are in fact tractable queries. They are easy, they are hierarchical. You see, we have these pairs dancing within another, you know, bigger entity that dances with something and so on and so forth. So that is hierarchical. This we can deal with. As examples of hierarchical queries in our syntax, look at the first one. The first one joins R and S on A, and then takes a difference with T. But now the interesting thing is that A occurs in all the relational symbols, right? Okay? So we don't have the situation where R is only A, T is only B, and S has both, right? All others are in fact variations on the same theme where we can actually have A and B not occurring in a relational symbol together, right? But they may be intertwined in some weird ways, the ways this language allows. What is also interesting is that negation and projection, which essentially means existential quantification negation, can appear intertwined in this query in some arbitrary way. So it is not necessary that negation only appears on relational symbols, but may appear on entire subqueries, right? What about non-hierarchical queries? Well, so this is the standard one we've seen before, but there may be some others. For instance, I take a join between R and S on A, and then I throw away the B from here, right? And then, well, sorry, I throw away the A, right? And then I take the difference with T, right? So here you see I can have a difference, and this difference acts in a way as our join with respect to this hardness results, right? So we have RST, but now they are connected differently, not only by joins, but also by negation. We can also take the other form, right, T minus the rest, and we can also mix them in any way we like. Yes?
The second line, where is the joining hand problem?
Here?
Yeah, you had this nice picture of the bridge. And what's the bridge here?
The bridge would be this.
So your definition should be taken as a metaphor, not as a mathematical definition.
Yeah. The definition you mean with the dance?
No, even the definition before that, right? A, B, C, I mean, you had the definition there.
Yeah, so this one. Yeah, well, I simplified it. The idea is this, that if you do joints, essentially the exact definition is this. You look at equivalence classes of query variables. And an equivalence class is defined for a variable is defined as, all other variables which are transitively equal to this by looking at the equality joints, but also those that are forced by difference operators, right? So the difference operator, if you take a query minus another query, it means you have to provide the mapping between the variables.
What I'm saying is the second line should not be taken literally, because it's not really a triple of relation symbols. No, you only have two relation symbols.
No, you mean here? It's RST.
RST.
It's RST. Oh, so you meant that. So we have RST, right?
Okay, I misread it. I'm sorry. You're right.
Dan,
So it's RST, yes.
is it as simple as saying that your notion of hierarchical means take the query, erase all the symbols and replace them by conjunction? Then that's a conjunctive query which is hierarchical in the sense of that.
Yes. With the only exception that in case, obviously, I mean, some tiny technicalities. If you have renaming operators or whatever, you have to look at query variables which are actually made equal by the query, right? Which may mean by means of transitivity of the equality, or may mean by mappings for the difference operator. But that's exactly the thing, which is falling back to the same characterization essentially, right? So let us look at these hard queries, which are, I guess, the interesting ones. So I will give you a few. I will try a few, sketches of proofs, right, to show hardness. I will start with a very simple one and go to a bit more complex ones to a bit appreciate the fact that not everything can be treated with the same, handled with the same stone. You throw the stone and that's it. All of them will fall down the same uniform way. And the idea is to do a reduction from the Sharpe-Hart model counting problem for a positive bipartite DNF. Right? The idea is you are given a non-hierarchical query in our formalism, then any positive bipartite DNF formula psi.
What is positive bipartite DNF?
So imagine a DNF formula, right? But every clause has two literals. One literal comes from a set and the other literal from another set. Right. So in this sense, it is bipartite because if you represent it as, let's say a graph, right, is such a graph, right? And then x's between themselves do not have edges, but they have with the y's from the other side, right? So you can have such a graph representation of it. And the idea is that you compute the number of models of psi, then you can use linearly many calls to an oracle for that computes for you the probability of the query, right? And the way you do it, you take the formula and you somehow generate a database such that the query applied on that database, gets the grounding of it with respect to that database is in fact your original formula, or a formula which actually helps you compute the models of the original formula, right? So that's the kind of general approach of solving these problems, at least in probabilistic databases. So the simple case is this: is the case of RST, right, where we have only joins, and so this is the query, right? RST, you join R with S and T, and then it's a Boolean query. So you imagine that this is just an exists A exists B. You quantify over A and B. And now we have this simple formula for the sake of the presentation with these clauses, and this is a positive bipartite 2DNF, so positive bipartite formula. So what do? You do this. You somehow, from this formula, generate databases such that, applying the query on the database gives you back the grounding would be the original formula. So what do? For R, we just create a tuple for every single variable in our set X. Right? In this case, I actually abuse a bit of notation. So I say I have the constant x1 and its variable is also x1, right? So this means that this tuple is in with the value x1, depending on the value of this variable, random variable. And x2 is with x2. For t, I do the same, but for the other set, for the set y. And for the S, and this is the essential point, we have a tuple in S for every single clause in our original formula. Why so? So that when we join R, S, and T, S guides which tuples in R are paired with which tuples in S. And that's the idea. It's very simple. So this T would mean simply true. This means that this table is in fact deterministic, whereas the others are not deterministic. So this one has 4 possibilities, right? Because we have 2 tuples, so each one can be in and out, and T the same. So if we actually do, using relational engines, we do the processing where we also propagate this additional information. We carry over the lineage or the grounding. At the end, we get actually our original formula we started with. And then obviously, right, if we can compute the probability of this using our oracle, and we assume that all the random variables have probability 1/2, we can then go back to our formula psi and compute its number of models, right, very easily. It's 2 to the n times the probability. Right, so it turns out that if you only look at positive queries, I mean non-repeating conjunctive queries, this is the only minimal pattern you have to deal with. And everything else falls back to this pattern, right? By, for instance, having additional joins that you can do with relations that can be just trivially filled with information which would not affect the final result, right? Well, in case of negation, things get a bit different. So this is a surprising case. I consider this query, which joins T and S, right? And then takes R minus this result, right? Where I throw away the B, right? So I only project on A. It's like I have the exists B in here, right? So I take R minus this. Now it turns out that for this particular query, the RST pattern that can give me hardness is enough to have just a single relation probabilistic. And the other 2 relations can be deterministic. This is because with this negation and existential quantifier, we simulate some universal quantification in there. So essentially what we do here to essentially recover the original psi, our input formula, as the result of our query, we do the following. Construct a database. So we fill in R, T, and S in the following way. For R, we just mention a row for every single clause we have in there, in our original formula. So we have the first clause and the second clause. In T, we essentially have a row, have a tuple for every single variable we have in our formula. Right? We have x1, we have y1, we have y2. And as it's, let's say, lineage or annotation, we use the negation of that formula. And in S, we essentially list which clauses have which variable. So we say that clause 1 has variable 1, x1, clause 1 has variable y1, 2 x1 and 2 y2. And this is deterministic, only this one is probabilistic. And what happens is that once you join T and S, you get the same information as in S, but where now the information, every row, will become annotated with the formulas of random variables coming from T. Essentially saying that clause 1 has x1, and this is actually its probability. So has x1 with a probability given by not x1, and so on and so forth. When we actually throw away the B from here, we essentially collapse rows that have the same value for A, right? So 1 and 2. And we get a negation of our clause. We get not x1 or not y1. For 2, we get not x1 or not y2. So what happens now, what we need extra, is to negate this locally, right? And then we go back to our clauses. How can we do that? Well, we take R minus this particular temporary result, and that would give us our clauses. And if we now also throw away A, so we project away A, we get a disjunction of these 2 clauses, which would be our original clauses, right? Right. For interest, okay, so as I said, this is actually hard already when T is the only probabilistic relation. And this goes beyond our understanding of positive queries, where we needed at least two relations to be probabilistic. A more involved case, which for interest of time I will not go into detail, but I only want to mention the following. We have a new query. Imagine this query, where S, this guy with two variables A and B, is actually on this side of the difference, and R and T are just in a product. You might think that this should be a very easy query because you don't have a join. So the only correlation you can create in there between the variables in the input formula would only be because of this difference, because the product just blindly takes everything from R paired with everything from T. But it turns out that this difference is enough to actually ensure hardness. For that, in fact, all relations have to be probabilistic, and the argument is a bit more involved. But I'd be very happy to talk with you about this if you'd like later. So how can we deal in general with the queries? Well, it turns out that if we look at RSTs, we look at possible trees we can construct with RSTs, right? With the variables A and B, we get very many possible patterns, right? We get a pattern like this, right? Where we join a relation over A with a relation over B, and then we join it with AB, a relation over both AB. Or we can have A and B with a difference. This is meant as a pattern in the sense that obviously here may be an entire subquery. On the other side will be an entire subquery as well. Right? There are very many patterns. Well, some of them are reducible to other patterns because, for instance, joints are commutative and associative. So we don't need to consider, for instance, this pattern and that pattern. If we show reduction for this pattern, then the other pattern will follow trivially. But nevertheless, in case of the difference, the situation gets a bit hairier, right? And as I showed you before, there are different reasons for why hardness can be achieved. It's not the one single reason, right? And it may differ in the number of relations that have to be probabilistic and so on.
You have to construct 48 reductions.
As I mentioned, some of them fall back to the others, so it is very easy. The argument is very easy. You just say, holistically that, well, this is treated the same as the other. But it is true that there are still a handful of them left, which actually have to be treated differently. It may be possible that a more general argument can be made for a larger class of these patterns, but then we'll not be able to distinguish very precisely on how many relations are probabilistic or not. And we wanted to look into that, and astonishingly, although all these queries are hard, they are hard under the assumption that in general the relations are probabilistic. If you start looking into it and then realizing that way, in my query, if this relation is deterministic, for instance, then suddenly the query becomes easy, right? So it turns out that very, very few cases out of the all possible cases we have here would really be hard in the sense that, if at least one relation is probabilistic, then the query becomes hard.
So are you saying you have a refinement of the dichotomy where you can also tell for which probabilistic relations you get the hardness?
Yeah, I think it can be done. I don't have it written down, but I reflected about this, and yes, I think it is possible based on the results. I did in general. What comes out of the reduction? Yeah. So, and then how we basically get the queries?
Come out from reduction. Reduction is a negative result. I can have to have a positive result.
Yes, but
yeah.
You have to have a matching positive result. Essentially adding more tractable cases for non-hierarchical subject to this classification.
You're right. You are definitely right about that. So what we had to come up with would be an algorithm that actually provably does it in polynomial time for cases where we say, okay, if these relations would be deterministic and only that probabilistic, then we can do it. You are right about that. Yes. Thank you. So what happens, well, unsurprisingly, if we have a pattern and we have our query, let's say, the way we actually look at, we look at the matching. We try to see whether we can actually find a matching from the nodes in the pattern to the nodes in the query, such that, A would be mapped to a relation that has a variable A, B would be matched to a relation with variable B, and AB with something with AB, right? For any pair of A and Bs, right? We can come up with. And if such a matching exists, then we can say that we can actually show for that query that is hard. Essentially what happens is that the grounding of this pattern, right, the lineage of it, would be the lineage of that query, right? So all other relations are filled in a way that would not disturb this the grounding of the pattern. Good. What about the easy queries? So for the easy queries, the way we do it here, which somehow the message, let me put it this way, the message is a bit as follows, right? Dan showed you before that for some queries, if you really want to get tractability, you have to go beyond the propositional formula methods, right? So the ones that actually work on the grounding, right? It turns out that for the tractability results we have here, these propositional methods are enough, right? It just means that the language is so that, you know, it doesn't need to go beyond that, okay? So what do we do then? We take the grounding of the query, and essentially we show that we can compile it into an OBDD, which is an ordered binary decision diagram in polynomial time. And then once we have this, we can easily get the probability of this, right? And then using what also Dan mentioned before, namely that the probability of this grounding is the same as the probability of the query, we then get essentially the probability of our query, and we actually solve the problem. So yes, 5 minutes, yes. So what are the difference from existing tractability results? So if we now look at non-repeating conjunctive queries, for instance, that is, we take away the negation, and that's everything we take away, then we showed previously that the grounding formulas are read once. What does it mean? It means that we can essentially, you know, in a lifted way, follow the structure of the query, of the join query, and produce a factorized representation of this grounding formula, right? Which is read once. Yeah? And now, if it is read once, what exactly means read once? Imagine a propositional formula where every variable occurs once. Okay? It cannot occur several times. So then it's very easy to compute its probability. And in fact, it admits OBDDs that have linear size in the number of variables. But in case of our language with negation, the grounding of formulas, grounding formulas are not read once. And I will show you an example for that. And they nevertheless admit OBDDs of size linear in the database size, but they are exponential in the query size. And this exponent actually can grow with the number of intertwinings of existential quantifiers and negation operators. So the idea is as follows. We start from hierarchical queries, and then we essentially transform them into a more flexible relational calculus, existential relational calculus, where we have a disjunction of disjunction-free such existential relational calculus queries. And then we show that each of these term is in fact hierarchical in a much stricter syntactic sense. Essentially, it simply means the following. It means that if we have an existential quantifier on a subquery, then this x, which is quantified here, must occur in all relation symbols there. So because of that, we get this independence, what Dan showed before, that is for every distinct value of x, right, we have an independent subproblem. Then we need a certain property called consistency of our quantifiers, namely that all our terms must have the same order, the same nesting order of the quantifiers. So you say exists A, exists B, must be also exist A, exists B in the other case, right? If you have exist A, exist B in one case, and then exist B and exist A in the other case, then it will not work. Why so? Because if we have such compatible orders of the quantifiers, then for every single guy here we can get an OBDD, and the OBDDs for each of them will have compatible variable orders over our random variables. So then we can smash them together very efficiently. And when smashing them together, the OBDD we construct will still have a depth which is linear in the size of the database, but the width will increase exponentially with the query size.
Quick question. Yes. Do you also need to have the same quantifiers? I mean, do they have to be in the same order and of the same type, existential or universal?
So in my case, they are all existential because I'm only doing the translation so that I end up with an existentially quantified thing. So I don't push negation past existential quantifiers. So I will give you a very quick example. Imagine this query, right? R times T minus U times V. And then we project away both A and B. And these are our relations, which essentially say I have 1, 2, 1, 2 in every single relation. 1, 2, the tuples. So what I do, I take the product of R and T, right? Product of U and V, and when I take the difference, what I get all possibilities. But where I say R1 T1 from the first combination of R and T, and not U1 V1, or not U1 V2, and so on and so forth, right? If you look at this grounding, this formula, propositional formula, then regardless how you try to massage it, you cannot get a read once. And in fact, if you look at the graph of the formula, it has a P4, a path of length 4, which is a proof that in fact it cannot be read once. So what can we do? We do the following. We take the query, we rewrite it. The way we rewrite it is we essentially we essentially break this difference of a product into difference of components of this product, right? And we generate a disjunction. And then, as you can see now, we can separate out those parts that talk about B from those that talk about A, right? So we can do them very efficiently, and the order of the quantifiers will be exists A, exists B in both cases, right? So I will get the grounding for Q1, which will be this one, which is a read once, because this one here is read once, and read once is this one, so I'll get also read once here. So now, if we construct the OBDDs, will be just a linear size OBDD for psi1, one for psi2. They have compatible orders, because the order of the quantifiers was compatible, right? And then I can put them together very efficiently. Great. So I will just finish with this slide, okay? To give a picture, a general picture of what's going on with this hardness results. So there are some known dichotomies in this space. They were started by Dan, right, with non-repeating conjunctive queries, then with union of conjunctive queries. We looked also at cases with quantified queries, such as division queries, or set comparability, setting comparability, when we actually, the queries look at arbitrarily sized sets from the data and compare them. And we also look at ranking queries. Ranking means essentially you'd like to look at the results and only rank them by their probability, right? To say this is the first, this is the second, this is the third. It turns out that this problem is easier than the problem of exact computation. Why? Because in order to rank, it may be that an important subproblem will be shared by all these tuples, right? To compute the exact probability of every tuple, it may be that you have to solve a hard problem. But if that hard problem occurs everywhere, you can uniformly ignore it. Okay? Okay. So that's the way we can do that. So in general, it turns out that the hierarchical property is not enough if we want to add union, I mean disjunction, to our language, right? And there are cases for that. I will not mention now for the interest of time. And in case of full relational algebra, we cannot hope for anything, simply because if you have a union of two equivalent queries, but one is hard and one is easy, we cannot decide, right, the equivalence of them. So we cannot say in general that, you know, our overall query is destructible. And that's and that essentially means that we cannot come up with a syntactic procedure to decide that. I still believe that in general the queries have this separation of easy and hard. Okay, thank you.
Questions? Yes. Moshe?
I have a philosophical comment. The classification into data complexity and expression complexity was not meant to say that one can ignore the size of the query. To the contrary, it says that the size of the query plays a critical role. Yes. It was not giving people permission to ignore a very important part of the query evaluation.
We mention you all the time. We say, well, you know, Moshe told us
I did not give you a blank check to ignore complexity theory.
Yes. So the complexity we have here is essentially, you know, size of the database times a parameter 2 to the power of something which depends only on the query, in a sense, right? So, okay, this can be in fact large. It is true, but I think it would be useful indeed to look into which cases are in fact not so hard. And I can give you one. For instance, if all existential quantifiers by formula are outside, are at the outermost level, and I allow, you know, negation inside as much as I like, then it is only 2 to the power of the size of the original query. And this is perhaps doable. If I have a lot of alternations, then this approach will obviously blow up in the size of this.
My point is that your query compiler is supposed to decide how to do this, must take the things into account. You
Yes,
cannot say,
yes.
I don't care, it's a complexity, not to worry. It's only 2 to the 1,000, not a problem.
Yes, no, you are definitely right. I'm actually more of a systems person than person who would discard this,
You sure could
right?
fool me.
Yeah, but I have to say that it is rather hard to write a query which actually would have 2 to the 1,000. I would say, right? You'd have to be very careful how you intertwine the existential quantifier with negation to get to that. And I think that this can be computed, in fact. So you know what is the exponent there, and you can decide based on that exponent if you go ahead with this particular solution. Yes.
All right. Well, if there are no other questions, you can.
Yeah.
The very last comment where you said there should be a general dichotomy.
Yeah.
Is there a relational algebra query which has been looked at, people have tried to work on it, and it's not known whether it's easy or hard?
I have one. Yeah, I can write the code.
Yeah. Please go ahead. No, we have a board.
For x1, y1, 2 by 2, s, just one symbol, x1, y1, or not s, x2, y1, or not, sorry, s, 2 by 2, or not s, which one is next? X1 by 2. So if you think of the variables as being placed here, x1, y1 by 2, y1 by 2, then you get a positive s for these two edges, and then negative s for these two edges. And we don't know what the complexity of this query is, where it's key, because he was commiserating with me trying to find the complexity of this query. We know that this query can be computed in polynomial time over symmetric databases in a very complicated way. We don't know what the complexity is on over general databases.
On this great note, so thank you. Let's take a break for coffee. We reconvene at 10 past the hour, 11:10, please.